Diffie-Hellman is used to exchange shared secrets over a public medium without actually transmitting that key value across. Now we're going to show an example here with Alice and Bob, and we'll talk about how Alice and Bob will end up with the same exact shared secret key to perform encryption, but they're not going to send that number, that key value, across the wire. To do this, we need a little bit of information. Okay, so first of all, here's what we need. We need to have a prime number that is going to be our p-value. That's 31. We need to have a base number. That's also a prime number. That's going to be 13. Remember, a prime number is a number that is divisible by 1 and itself. All right, so the next thing that we need to make this happen is a secret value on both Alice and Bob. They're not going to tell anybody this number, though. Now, the secret value, we're going to give this a lowercase a value, will be 8 on Alice, and on Bob, the lowercase b is going to be 12. Now remember, they're not going to tell anybody what these numbers are. We're going to calculate a shared value that will actually pass across the wire using the formula g to the a mod p on Alice and then g to the b mod p on Bob. Let's start with Alice. If we were to use that formula, we're looking at 13 to the 8th mod 31, and we're going to come up with a value of 7. We're going to take 7, which is our uppercase A value on Alice, and send that right across there to Bob. The next thing that we're going to do on Bob is repeat that process. We're going to do 13 to the 12th, mod 31. That's going to give us a value of 8, and that is our uppercase B value on Bob. He's going to take that value and send that number 8 right over there across to Alice. Now Alice is going to take that B value, and we're going to use that same formula, B to the A mod P in this case. So we're going to come up with 8 to the 8th, mod 31, and we get a value of 16. Now guess what? That's our secret key. And we're going to come out with the same value using different numbers over on Bob. Let's see how that works. So Bob received that uppercase A value, that shared value from Alice, and that number is 7. So we're going to do 7 to the 12th, mod 31, and there you have it. 16 is the value that we come up with. 16 is our shared secret key, and both Alice and Bob can now encrypt traffic between each other using that key value of 16, and everybody's happy. Now, in this example, we used a very small number, or several very small numbers, to illustrate how this algorithm works. Obviously, in a real-world environment, we're going to be using much larger numbers to compute the key. Now, with Diffie-Hellman, we have what's called a Diffie-Hellman group. The higher the group, the more bits we use in calculating the key. So, in Diffie-Hellman group 1, we have 768 bits that we're going to use to compute the key. Diffie-Hellman group 2, 1024, Diffie-Hellman group 5, 1536, and with 14, 15, and 16, you can see how those bit values are increasing there as well. Now this is how they're supported on Cisco iOS. Cisco iOS also does support the NSA Suite B cryptographic values, which we can use elliptical curve cryptography for Diffie-Hellman groups. That would be groups 19, 20, and 24. Again, this is just an example of how we use Diffie-Hellman to exchange shared secret keys over a public medium without actually exchanging the key values.